Hi everyone, in this video I'm going to showcase what I've been working on recently, which is a reliable and optimized way of removing particular instances from a large open world environment, even in runtime, but it's more focused about server restart time. So what my theory, or let's say the concern, was that what if I, let's say, create a big open world landscape on a, let's say, 100 square kilometer landscape, and I quickly gather up, let's say, 1 million trees in my open world environment. I, let's say, do a multiplayer game, so let's have 10 people running around and chopping down trees, etc. And then let's say that I do a method where if they chop down the trunk of the tree, then I prohibit the tree from respawning. Now, of course, if you watch the previous videos, you know exactly that we are not working with actors. We are swapping the foliage instances in real time based on line tracing, meaning that we swing our axis, it hit a tree, and then we're swapping over to an actor. We deal with the actor, and then we're swapping it back. Now, what I was dealing with is a situation where I say, okay, they remove the trunk, they don't want this tree to be respawning, or let's say they build something from it. Now I can create some kind of mapping where I can store basically the data, meaning that I can do a map where I store, let's say, the transform of the actual instance, and the component name of that instance, meaning that right here, let's say it's going to be this one, component 0, which is the tree, and it's going to be the instance, I don't know, 10. And obviously I can't just store instance index because I can't remove them by index, exactly because in instance static meshes in Unreal Engine, at least 5.3, and it goes to hierarchical instant meshes and foliage instant static mesh components. I don't know if it's the same with the normal instant static meshes, meaning PCG generator and instant static meshes, but foliage instant static meshes, which is exactly for foliage, how it works is that it's index shifting. So if I have an index 9 and I remove this, then index 10 becomes index 9, index 11 becomes index 10. So everything shifts one below. Now or one in the direction of the removed asset. Now or the remove instance. So because of that, I cannot just say, okay, I'm storing index 8, 10, and 11, because if I remove 8, then 10 and 11 already is not valid anymore. So yes, sure, that's an issue. But also the other issue was that what if I have, let's say, 1 million trees in my open world environment, and then 100,000 of them is already being cut down by players, and the server is restarted? What's going to happen? Because in a linear kind of scale, what you would happen is that you have a map, you store, let's say, 100,000 entries in your map, which is going to be like an object ref or a name of the component. It's going to be a map of a reference, object ref or name reference, to transform. So you would look up the map, and every single cut down resource from the map, which is in this case 100,000, you would need to compare all the instances in all the components, meaning that if you have a 1 million trees, you cut down 100,000, that means 100,000 times 1 million. At the end, you're going to look up 1 billion entries or 10 billion entries or 1 trillion entries, It's not viable. It takes minutes, if not hours, and of course, Unreal Engine would crash out. So it would not work, basically. Because my theory is that once the server restarts, you have to remove those instances that are not supposed to be there anymore. Because obviously in Play Editor, I have all these trees here, right? But when I move into the game, actually, let's say I move into the game, and then I have these trees right here, right in the beginning. If I look at this one, and I mark also this one, and let's say I mark this, and I mark this. So all these should be removed next time I'm logging in. Okay, we wait the next word save. There we go. So we close the game, and then I go back into the game. Now it says that we have removed some items. If I go back, as you can see, all these trees from here are missing. They're not there anymore. Last one is still there. I have some issues. Like I said, I still need to fine tune it, but it's removing these items that I don't need anymore. And in a large scale, if I have a million trees, that's gonna be costly. And I've been looking up on YouTube about a technique called spatial hashing, which basically used usually in collision settings, graphics environment, terrain loading, open world, grid cell loading, basically, and stuff like that. So that's where the idea comes from. But we can use it here because what I've been working on with ChatGPT for the last, I think, 18 hours. If you look at my history, I could do this scrolling, or like I could scroll here for 15 minutes slowly, because I've been doing this for the last 18 hours, like this whole removal of stuff. And what ChatGPT been recommending me, and basically I did some simulation with GPT. Obviously, it's not accurate, but GPT kind of knows the computational overhead of this stuff. Is just simple simulations, and we call this spatial hashing for instance removal. And how does that work? Is that in Unreal Engine we created some structs. We created a bucket key, which is a XYZ integer, which kind of responds to the grid location of the actual item or the instance, sorry. The second struct that we created is a so-called, where is it? Removed foliage right here, which contains a object ref, but in our case it's a string of component name, because in save games sometimes hard object references can be a little bit changed with the saves and not always reliable. So I rather convert that to a display name and store it as a string, and then a location. So string and a location. So the foliage component name and the location. So we have the bucket key XYZ, we have the foliage instance, which is a foliage component to location, and the last one that we created is going to be the bucket itself. Now, why it's a struct of bucket is because in Unreal Engine we already run, even though I'm a beginner, in some limitation in terms of blueprint editing, meaning that if I create a new variable and I want to have this one to be, I don't know, a string, like a key, into an array of something, I can't do that. Now, let's say I create a map, okay, right here, map. I can have a single to single mapping, meaning I can create here a bucket key 2, like a struct, bucket key, singular struct item, into a singular struct item. So I could do a, right here, removed bucket. So a bucket key to bucket, but I cannot have the bucket as an array. So you cannot have a single to array mapping. So the map entries should contain one single to an array, each single as a key and each array as a value. You can't do that in Unreal Engine. And because of that, what we do is we wrap the array into a struct. So you have the bucket key, which is singular bucket keys. You have instances, and each instance is a struct, and you have the bucket itself, which can be an array. So we do a instance struct array, meaning that this struct is wrapped into an array and is stored in a struct. So then you can have a bucket key bucket struct, but in a sense that your bucket itself is not going to be singular, but it's going to be an array. So that's kind of, we cheat the whole system. And then how we do it is that in the game state, of course, I'm loading this kind of mapping, which in our case is a bucket key to bucket mapping. I'm loading this in the game state and reaching the game state to load it. And of course, I created this save game. So basically, I store this map into the save game and then load it to the game state. And then from there, I'm loading into an actors or whatever I want to use it. In this case, it's a actor that takes care of everything, and that's the two main part that it takes. Bottom part is basically adding it into the mapping, and the top part is that retrieving from the mapping and deleting from the open world. So let's see the first one, how we add it. Now, how we add it is we trigger a interface function, not related or how I do it, whatever. Has to have an object ref, because I take the object ref and get a display name out of it, and has to have a transform. This says that this is the component object ref. So in this case, let's say the tree, which is component 0 in here. and it's going to have the transform location of the particular index that I'm removing. So in this case, let's say I'm removing index 4, which is this exact transform here. So what I do is that basically, let me just go back. Yeah. So what we do here is that we get the transform location, we convert it to a transform location node. So we take the transform and convert it to a vector, and then we break the vector. We get 3xyz. We divide it by 100. We convert with floor into integer, and that would make our bucket key. And then we make a make struct bucket key. And like I said earlier, the bucket key xyz integers like this. So we create our bucket key. Just move this one here. So we create our bucket key, and then simultaneously we take the display name, convert it to a string, and add it into our instance struct. So it's going to hold the name. And of course, if we are here in the vector anyway, we are doing it the location here. So yeah, we made a bucket key, we made a foliage instance, and now what we do is that we do a branch which says find in the mapping, which is right here, which is the map that contains bucket key to bucket, find in this map, and actually bucket key to bucket, but the bucket is an array of instances. So even though the Unreal doesn't let you do it here, we did it with the wrapping. So first it tries to find in the mapping from the bucket key, meaning that you're trying to add something. We created a bucket key for it, and we're trying to find if it exists already in the bucket or not, or already exists a bucket key like this or not. Because if a bucket key already exists like this, then what we do is that we're going to say, is it already exist? Sure. Then we take, and again, we run into the second Unreal Engine limitation, which is if you have an add node like this, like an add array node, you can have an input for it, what array you would like to add instances to. You can have the instance that you would like to add it to, but you don't have an output. Okay, you have an integer value, the index of the newly added item. I don't care about this, I care about the array. Because if I don't have it as a variable, because I don't want to declare it as a variable because it goes through a loop, so it's temporarily, I still have to do it because it doesn't have an output. But either way, so what we do is that we try to find in the bucket, we try to find in the map a particular bucket based on the bucket key. If we find it, then we are going to set a temporal array. The temporal array is going to be a break struct remove bucket. So we take the bucket that we try to, like literally here where it says that is find in this map a particular bucket with this key. Did you find it? Yes, sure. So break the bucket. You're gonna have an array of instances. Add to that array of instances the freshly added new instance that we would like to add it to. So this instance that we just said, okay, add it to the removal kind of, removal list. So add it there, and if you did it, you added it into the array. Because you break it, you have to make it back. So make back the bucket based on the array that you just, added, and then we add it back into the map. So basically we found the bucket with the bucket key in the map. So we break it, we take out the array, we add the new instance to the array, we package back the bucket, and then we add it to the map back. That's the main logic. If it doesn't find it, it doesn't exist in the mapping, it doesn't exist this bucket key, then we're going to clear the temporal removal for each array value, which we did here, but it's not related. And then what we do is that we add into into the array, we create this temporal array again, because you cannot have an output of an add node. Otherwise I would not create a variable for this. But we're going to clear it, and then what we're going to do is we're going to add into this temporal kind of array. And then we're gonna make a bucket, because the bucket doesn't exist. We didn't find the bucket, so we're going to make the bucket based on a fresh new array. And the bucket, we're going to add it to the mapping. Simple as that. It's not really overcomplicated. And then the removal of it, that's how you add buckets and arrays in the bucket and a bucket in with a bucket key into the mapping. And then how you actually retrieve it is that you are going to, whenever your word starts or the server starts, you're going to basically you have to, as up to you how you do it, you just have to save this mapping, this kind of, you know, map which has the bucket key to bucket mapping, bucket key to array of buckets. I mean, yes, array bucket key to bucket, but the bucket itself contains an array of instances. Yes, thank you. So you need to somehow get this mapping up and running each time the server loads. In my case, again, I'm saving it here in the game save, and then I'm loading it into the game state, and from there I'm loading it into the actor. Doesn't matter either way. I loop through every single foliage instance static mesh components. Let's say each array element here gonna be a component. So in this case, it's gonna be a tree right here, and then it's gonna be another tree and another tree type, or I don't know. This is a rock. This is a tree. This is a something else. You get the idea. So for each of them, I'm looping through them, and I say get each of the instance count of them, which gonna have a total instance counts for each component -1. So subtract 1. There's going to be your last index in a for loop, because I'm for looping the loop body, meaning that you have 3 components, let's say tree, rock, and coal, and each of that gonna have like, I don't know, 1000 indexes. So you're gonna get the instance count, you're gonna get the last index, so -1. That's gonna be your last index in a for loop, and the index of the loop body, so the actual individual index, you're gonna take it, and you're gonna take the last index minus that index, and that's gonna be your get instance transform. I might need to edit this, but the idea is there is a reverse indexing. You're not going from bottom to top, you're going from top to bottom. I mean, from last to first. So you're not instancing it from first to last, but you go reverse. You first find the last one and then you go reverse. That would be the idea that you do it, because again, it shifts. So if you remove something from it, like you remove, I don't know, let's say you remove instance 1, then instance 99 will be 98. So rather go from the top and remove other reverse. But either way, so what we do is that, again, we looping through each component, get the instance count, reverse loop it, and then inside the reverse loop we get each of the instance transforms. So each instance index we get from the original component, we get the transform, we convert it to a vector again, we go through the same stuff. So we break the vector, we divide it by 100, convert with a floor to an integer, make our bucket key, and now we're going to have for each instance component index an individual bucket key. And now we're gonna say find in the mapping that we have this particular bucket key, and if you found the bucket key, that's true. Then if it doesn't true, it's false. That means we don't need to remove the item because it doesn't exist there. But if it's true, we found it, then what we're going to do is we're going to execute another for loop inside a loop, which is already in a loop, and that's going to have an array for the break struct removed foliage bracket. So what we do is say, okay, find in the mapping with the bucket key the bucket value, and if you found the bucket value, which is by the way an array of instances, then break it, get it as an array, loop through the array of instances in this bucket, and then basically find the foliage component name, which is supposed to be equal to the originally looped array element, which is in this case a component object reference, obviously, because we looping through each object reference with this loop and with this loop. So then we compare it, the original component object ref display name, we compare it with this one, and again it could be, if I store it a hard object reference, you don't need to get display name, but I like a string comparison. And then I also took the location, which I saved in each individual instance. So what I can do is I take the open world instances transform that we took, that we made the bucket key with. I take that vector and I basically divide, subtract from the instance, I subtract the open world vector and I do vector length squared. And I say if it's less than 4, then we have to remove it. And then what we have to remove? We have to remove the last index. And we have to remove what? We have to remove the looped component object ref. And that's what it takes basically. And even though that it seems more, because what I could do is I just store the transform. I store the object reference name, and then every time we load into the game, I just loop through every single instance and I say, is this transform matching? Yeah. Is the name matching? Sure, remove it. But that's literally a linear lookup, and it's going to, and I'm showing you why it's not working that way. I did some simulation with GPT. I've not been testing it out like real time, but the idea with the spatial hashing is that if you have, let's say, 100,000 trees, okay, so let's say you have 100,000 trees and you already mined 10,000 trees out, then in order in a linear setup to look it up, whatever has to be removed is that you take 100,000, you multiply it by 10,000, and then it's going to be equal like 1 billion, okay? So you need 1 billion real-time lookup in order to determine what is that 10,000 one that you need to remove. But with spatial hashing, you only comparing it to grid cells, meaning that you have 100,000 trees, you removed 10,000 trees already, and that's going to mean that you look up 10,000 times, I don't know, 15 or 30, because that's the grid size, and you're only looking up that much. So worst case scenario, here you're going to have 3 million lookups. So you have 1 billion versus 3 million. You get the idea. So that's why spatial hashing is way better. And then of course all night I've been up with GPT and trying to go through this kind of technique and why it's okay and it's not okay, and etc. And I did some simulate as well. This is how it looks like in terms of performance factors, is that in a native way, which again would be you creating a transform and a display object, let's say in a map, so a name to transform map, and you would look up that way that I explained earlier in a normal way, like you would have a map of, I don't know, object ref to transform, and you would look this map up each time instead of this spatial. What it would do is that looping all foliage components obviously same on both of the spatial and the normal. Iterating through each instance, same. Again, it's no difference here. Look up the removal check. Now this is different because here what you have to do is that R is the number of removed instances. So you need to look up all the removed instances. But in this one, you just look up the bucket key, which is a 01, and then you look up how much the bucket key is, which in this case, the number of removed instances in the correct bracket. String comparison is same. You would compare the string with all the removed instances, or you would compare it to the number of correct bucket entries. So that's kind of the whole thing, is that total removal checks in the native one is R times M, which means the number of removed instances times the total number of components, total number of instances per component. So if you have 100, that's what I said, if you have 100,000 trees and you have 10,000 removed in a normal way, that's 10,000 times 100,000, so 1 billion. But if here you have a B times M, which means that you have a number of removed instances in a correct bracket times the number of total instances per component, so you're still multiplying 100k, sure, but you're not multiplying with 10k total removed trees, you're multiplying with 30 possible options, and that nets you, let's say, 3 million total lookups. And let's say I simulate this in a really advanced crazy numbers. So what I did is, let's say I have 10 million total trees, I mined 1 million of those trees out, how much you would take in both ways. And what what GPT said is crazy. It said that in a native environment, it would take 10 trillion comparisons, 10 trillion comparison, and that would be completely unusable. Unreal would freeze instantly, and it would take 23 days to actually do it. So 23 days. But in a spatial hashing environment, it takes 30 million total comparisons, which could be executed in 8 seconds. And of course, this can be parallelizable and game ready. But the whole thing about this is that basically it goes through everything. You have instances of struct, you have bucket keys of struct, and you have a removed foliage bucket which contains array of instances. A map of hashed grid cells, removed instances within them, fast lookup, very scalable. And the workflow is that you get a transform, generate a bucket key, break vector, right? It goes through everything. And that's the crazy part, is that for each foliage component, get an instance counts, reverse loop, use the get instance transform, location, make a bucket key, look up in the map. If bucket exists, then you look through, because your bucket key is basically the same bucket key that goes for the open environment inside the loop. So you don't really need to compare it with 10,000 entries in a map, because you actually looking up if in the open world it exists or not in grids, and each grid gonna be a bucket, you know. So let's say your open world gonna contain 1,000 buckets, or I don't know, 50 buckets, 100 buckets. I have not tested this totally yet, but definitely I've been doing this for 18 hours with GPT, and GPT 100% convinced that this is the only viable way that I can do this whole open world environment through this, right? So that's it for this video. That's what I've been working on: spatial hashing and removal of large number of trees in runtime. And this is great because if I log into a game where I removed certain items, like for example at the beginning of the video I removed some trees, if I log in, these trees not gonna be there either. And same goes for the foliage. So if I pick some foliage up and then I pick each of these foliage up, whenever I log back into the game after I have been logged out, these are not gonna be there. But of course this is not related to the spatial hashing, because I just make these invisible and visible with material masking, which has nothing to do with the spatial hashing that we did. But yeah, it's most likely for the trees, which are obviously collision enabled, so I somehow have to remove them completely. I can't just make them invisible. I need to remove them if I don't want them to be spawned back. That's it for this video. I hope it was kind of my logic flow and how I did it is helpful to someone, and I see you in the next one. Take care. Bye bye.